Okay, de Moivre's theorem. This is section 1.3, complex numbers, year 2, called pure. First of all, let's state the de Moivre's theorem. You will need to learn how to prove de Moivre's theorem, but we'll do it in a separate video. We'll use proof by induction for positive integers. Okay, so if you can raise a complex number to a power, then you can actually apply, in this particular instance, the rules of powers. So here's the product. So you raise r to the power of n. So you distribute the power between r and e to the power I theta. So when you multiply, you get e to the power I theta to the power of n. So over here, the rule of indices can be applied. The two powers need to be multiplied, and you're going to get r to the power of n and then e to the power of I n theta. So you get a complex number with modulus r to the power of n and argument n times theta. So if you want to state this in trigonometric form, it's simply r to the power of n and then cos n theta plus I sine n theta. So you raise the modulus to the power of n and you multiply the argument by n. There you go, forgot to put n over here. So this is our de Moivre's theorem. This is quite an interesting result. If you raise it to the power of -1, your complex number, you're going to get r to the power of -1, e to the power of minus I theta. And if r is equal to 1, then you are going to get cos theta plus I sine theta to the power of -1 will give you the result of cos minus theta plus I sine minus theta, which is the complex conjugate of the original number. Okay, so that's quite something unique we will be using a few times in the future. Okay, so we are going to have a go at applying de Moivre's theorem to simple calculations. We're going to find the answer to the following calculations. Doesn't say which form they want the answers to be given. I think it's going to be just in Cartesian form. Okay, so over here you could see we're going to apply the powers first. So applying the power to this complex number, and it's clearly a good complex number because in the correct form. So it's got a plus, so you can just rewrite it by multiplying the argument by 5. Okay, so you're going to get cos, and let me just do 5 times 9 pi over 17 is going to give you 45 pi over 17. So it's cos 45 pi over 17 plus I sine 45 pi over 17. So at the moment you could leave it like this for now, or if you wish, you may want to find the equivalent argument that falls between minus pi and pi, which is up to you. I'm going to leave it till later because once I've divided by the denominator. So in the denominator, we have to raise this complex number to the power of 3, but it has a minus over here. So I'm going to, first of all, incorporate that minus into the argument. So that tells me that I must have a complex number with minus 2 pi over 17 plus I sine minus 2 pi over 17. There you go, to the power of 3. So carrying on, I will just copy the numerator as it appears. 45 pi over 17. Okay, now I'm ready to multiply my argument by 3. So you're going to get minus 2 pi over 17 multiplied by 3 gives you minus 6 pi over 17. So the complex number in the denominator is cos minus 6 pi over 17 plus I sine minus 6 pi over 17. Okay, so over here we're going to divide, so the arguments are going to be taken away. So subtract arguments. If you had a value of r, but these both complex numbers have modulus equal to 1, but if you did, you would need to divide them first. So it's 45 pi over 17 minus negative 6 pi over 17. So this is going to be 45, add 6, so 51 pi over 17. And 17 goes into 51 3 times, so it's 3 pi. So we have got overall the answer of cos 3 pi plus I sine 3 pi. Now, if you are asked to leave the answer in trigonometric form, that would not be adequate. You need to take the multiples of 2 pi. So clearly here you can only take one of the 2 pi's away to get cos pi plus I sine pi. Then that would be okay. However, we're going to evaluate it. So cos pi is going to be equal to minus 1. Sine pi is 0, so it's minus 1 plus I times 0, which is minus 1. And that is the answer to example 8. So now we are ready to move to example 9. Okay, so I made a mistake here, called it example 8, but never mind. We're going to leave the answer, evaluate it, express this number in the form x plus I y. Okay, where x and y are real values. So over here, before we can apply de Moivre's theorem, it's clearly de Moivre's theorem because you've got a complex number raised to the power of 7. So I need to know 2 pieces of information. I need to know the modulus, I need to know the argument, and you may wish to express this number in exponential form first or trigonometric form. I'm going to go for exponential form. So I like to always sketch my number to an Argand diagram. So it's 1 across, root 3 up, so root 3 somewhere here, 1 across over here. So 1 plus I root 3. So the length of the number is 1 plus root 3 squared, square rooted, that gives me the value of 2 over here, and the argument, so theta, let's call it theta, that's going to be arc tan or tan inverse if you prefer. This is root 3 over 1, which gives you 60 degrees, so it's pi over 3. So first thing to do is to rewrite what's in the bracket in exponential form. So let's put it as 2e to the power of I pi over 3. Raise it to the power of 7, you get 2 to the power of 7. E, multiply the argument by 7. Okay, so it's 7 pi over 3. This is 2 and 1/3 pi. So if you take away multiples of 2 pi, only one of them can be taken away to give you pi over 3 as the final argument. Okay, so 2 to the power of 7 is going to be 128. e to the power of I pi over 3. Okay, let's change it into Cartesian form, so we must write it in trigonometric form. So it's cos pi over 3 in brackets I sine pi over 3. So it's 128. Cos pi over 3 is a half, and sine pi over 3 is going to be root 3 over 2. Okay, expand the brackets, you're going to get 64. Add 64 I root 3. I guess you could say 64 root 3I, but then I would look like it's a little bit further away from root 3. So that is our answer. Okay, that takes us to exercise 1C.